In this lesson, we're going to incorporate thermochemistry with a familiar topic to us, stoichiometry. All right, so what you have to realize is that heat energy is actually part of the equation. If I look at a reaction like the combustion of methane, we can see that for every 1 mole of methane I get to burn in 2 moles of oxygen, I'm going to get 1 mole of carbon dioxide and 2 moles of water in that reaction. And at the same time, I'm going to get negative 890 kilojoules of energy per mole of that reaction as written. So what does that actually mean? So that means for every 1 mole, of CH4, there is negative 890 kilojoules of energy, or for every 890 kilojoules of energy, there's 1 mole of CH4. Also, for every 2 moles of oxygen, I'm going to release 890 kilojoules of energy, or for every 890 kilojoules of energy released, it's going to require 2 moles of oxygen to do that. We could also look at the products as well. For every 1 mole of CO2 that I produce, I'm also going to produce 890 kilojoules of energy, or for every 890 kilojoules of energy, I'm also going to produce 1 mole of CO2. And if I look at water, for every 2 moles of water that are produced, I'm also going to produce 890 kilojoules of energy, or for every 890 kilojoules of energy that's produced, I'm also going to produce 2 moles of water in this reaction. So what I can do is I could actually incorporate the heat as part of the reaction. So this reaction is exothermic. Heat is being generated. It's negative. It's being released from the system. So I would include heat as a product of this reaction, put it on the product side. And when I do that, this is called a thermochemical equation. All right, so let's look at some things we can do with these thermochemical equations. All right, if I take a reaction and flip it, so here I have our original combustion reaction where heat is a product, so this is an exothermic reaction. And I just reverse the reaction. I flip it around. The products are now the reactants, and the reactants are now the products. So what happens is the heat switches. Now the heat is a reactant, and this becomes an endothermic reaction. So I flipped it around, and I also have to flip around where the heat is, what side that's on. So if I look at this in terms of enthalpy of the reaction, I could see that the sign changes now for this, and it becomes a positive value. It's an endothermic reaction for this reaction. All right, so if I mess with the reaction itself, I also have to mess with the heat. So here I have the original reaction that gives us 890 kilojoules of energy. Remember, the sign is just showing the direction. So this is negative, so it's an exothermic reaction. It shows there's actually no such thing as negative energy. The sign dictates what direction that energy is flowing, whether it's out of the system for an exothermic reaction like this one, or endothermic where it's coming into the system, and it would be positive. All right, so let's say I just multiply through by 2. So instead of 1 mole of CH4. I'm going to have 2 moles of CH4, 4 moles of oxygen, 2 moles of CO2, and 4 moles of water in this reaction. So I also have to mess with since I've messed with the reaction, I also have to mess with the heat of that reaction. And that heat's going to be doubled. It'll be 2 times the negative 809 kilojoules of energy, which gives me negative 1780 kilojoules of energy per mole of that reaction. And if I cut it in half, instead of 1, I make it 1/2. Instead of 2, I make it 1, 1/2, and 1. I also have to cut that energy in half. So instead of negative 890, negative 445 kilojoules of energy. So this really highlights that heat is an extensive property. It matters how much you have, extensive as opposed to intensive, where it's just a part of it. It matters how in the reaction. All right, so let's do some problems. Looking at the stoichiometry of this reaction, for every 1 mole of methane, we get we're going to release negative 890 kilojoules per mole of that reaction as it's written. So the problem says I have 2.5 moles of methane gas and I burn it in excess oxygen, so there's no limiting reagent. How much is released? So setting that up, I have 2.5 moles of CH4, and I know that from this reaction, for every 1 mole of CH4, it's asking me about energy, so I'm going to get negative 890 kilojoules of energy for every 1 mole. And if I crunch those numbers, the moles cancel out, so it's negative 890 times 2.5. I'm going to get negative 2225 kilojoules of energy released. To do this in the correct number of sig figs, if I have 2 sig figs, it would be 2.2 times 10 to the 3 kilojoules of energy. So now it's asking how many moles of carbon dioxide are formed when 18,000 kilojoules of energy is generated from the above reaction. So I'm starting out with the energy. I have negative 18,000 kilojoules of energy, and I have to relate that to carbon dioxide in the reaction. And I know that for every 1 mole of CO2, there's negative 890 kilojoules of energy. So in this case, the energy cancels out and the negative sign cancels out as well. And that's going to give me 20.22 moles of CO2. And to do that in the correct number of sig figs, it'd be 20 moles of CO2 in this reaction. How much energy is released when 55 grams of methane are burned in excess oxygen? So again, I'm starting out with 55 grams, but remember in a reaction, it's about moles. This is 1 mole of methane, 2 moles of oxygen. So I have to first convert my grams to moles using the molar highway. So for every 1 mole of CH4, and if I take carbon and 4 hydrogens, so this is 12.01, 1.01, 1.01, 1.01, and 1.01. Add them all up, I'm going to get 16.05 grams of methane. So now I've converted grams of methane to moles of methane, and relationship in the reaction to the heat. So for every 1 mole of CH4, there's negative 890 kilojoules of energy. And crunching those numbers in your calculator, you should get negative 3,049.8 kilojoules. And to represent that in the correct number of sig figs, 2 sig figs, that'd be negative 3.0 times 10 to the 3 kilojoules of energy. All right, so let's summarize everything that we've learned from this. So we've learned about thermochemical equations where we could put heat as part of the reaction. If heat is released from the reaction, it's on the product side. If heat is needed for a reaction, it's part of the reactant side. In endothermic reaction, heat is on the reactant side. For an exothermic reaction, heat's on the product side. Okay. If I flip a reaction, I just change the sign of the heat. So an endothermic reaction becomes an exothermic reaction. An exothermic reaction becomes an endothermic reaction. Okay. If I do anything to it, if I divide or multiply, I also have to do the same thing to the heat. The heat is part of the reaction. It's an extensive property. It matters how much that I have. So what we can do with all, what I've essentially done with all this stuff is shown that heat is part of the chemical reaction, and I could use stoichiometry to calculate how much heat we're going to get or how much heat is going to be required for a chemical reaction.